In this video, I'm going to do an example of how to solve an indeterminate frame structure using the moment distribution method without considering side sway. The moment distribution method is also often called the Hardy-Cross method, after the American engineer that invented this way of solving structures. So this method is a very convenient and easy way to solve structures with high degrees of indeterminacy and high numbers of degrees of freedom. So if you recall, for force method, we always have to solve a simultaneous set of equations that's equal to the degree of indeterminacy of that structure. And for the slope deflection method, we always have to solve a system of simultaneous equations that has as many equations and unknowns as the number of free degrees of freedom of that structure. For the moment distribution method, it takes kind of a different approach by solving the entire structure step by step in a kind of continuously improving approximation that actually ends up with an exact result. So what we do is, for each free node, we lock them all to begin with. Then we successively unlock nodes, allowing them to go into equilibrium and applying the appropriate moments. Then we apply carryover factors that carry those moments to the other ends of the members, because of course if we apply a moment to one end of the member, that affects the other end of the member. And by doing this for all of the members in succession, usually more than once for each member, until we get smaller and smaller carryover moments, then we get the actual total exact moments at the ends of all the members. Anyway, we're going to see exactly how this works for this particular example, where we have a non-sway frame because we can't have any translation of any of these nodes. So only A, B, C, and D are allowed to rotate. So there's actually 4 degrees of freedom. So that would be 4 simultaneous equations if we use slope deflection method. So those joints are allowed to rotate. We're going to lock them all to begin with, and then we're going to successively release each of these joints until we kind of basically shake out all of the tension in our structure. So this is a non-sway frame because C can't move up because of AC. We assume that's inextensible. It can't move to the right because CDE is fixed on the right, and that is also inextensible. And same with D, it can't move up and it can't move to the right, so it can't move in X or Y. Also, peculiarity with this structure, we have different moments of inertia for all of the members, so we're going to take that into account in our analysis. E is constant. We have a distributed load on the top, and we have 2 point loads. I've put this point load here kind of as a distractor, because this point load on the node is not actually going to affect our analysis at all, because basically it's going to be carried in compression, in CDE, and it's not going to cause any bending. So since for moment distribution we assume that everything is inextensible, all of the members are inextensible, and we're not taking into account any of the axial deformations, the axial loads are not important to the analysis. So we're only really concerned about bending. Also to mention, our sign convention over here is positive to the right, positive up, and positive counterclockwise, like all of the videos on this site. But of course some people like to do clockwise positive. That's totally fine as well. You just have to reverse all of the signs from the way that I'm going to do it. So the first step for the moment distribution method is to find all the fixed end moments. And we're going to find that for each individual member. And of course, the reason that we find these fixed end moments is because when we start the analysis, we're assuming that every single joint is fixed. So if the joint is fixed, and if, for example, if C is fixed and D is fixed, and we have this distributed load on top, the initial moment that we're going to have at the ends of member CD are equivalent to the fixed end moments. That is, the moments that would be at the ends if the member was fixed, which it is. So we're going to find the fixed end moments first. Usually, since we're dealing with indeterminate structures, when we're finding the fixed end moments, because both ends are fixed, we use a table that shows us what those fixed end moments are. So for AC, we have a point load that's right in the middle of the member. And if I look to the table, usually you can find it in the back of your textbook, we find that the fixed end moment is PL over 8. I'm going to show what that looks like in a minute. But if I just sub these in, so P is the load, that's 12. L is 6 for this member, and 8, and what we get here is 9 kilonewton meters. And what direction is that in? So if you look in your book or at a table of fixed end moments that you can find on the internet, then you'll see something like this, where P is halfway in between the two ends. Okay, and you see these two ends are fixed. This is L, and you'll see they show you what these moments are. These are the reaction moments at the end of this beam. And for this particular case, you'll find that this is PL over 8, and this is also PL over 8. Now we find the direction based on our sign convention. So on the left side here, this is counterclockwise, so that's going to be positive. So this AC is on the left side of this member if we look at the 12 as being down, right? If we twist it to look like this. So that's going to be positive 9 kilonewton meters, which is counterclockwise, and FEMCA, which is at the other side, is going to equal negative 9 kilonewton meters, which is clockwise, which is equivalent to this one here. Then if we look at CD, which has a distributed load, the distributed load fixed end moment situation looks like this. So we have our fixed ends. And if we have a uniformly distributed load on this member of W and a length of L, and we look in here, we're going to find that our fixed end moments are WL squared over 12 on each side. Positive according to our sign convention on the left, and negative according to our sign convention on the right. So we do FEM CD is WL squared over 12. We're going to get, for this one, our W is 6 kilonewtons per meter, L is 8, so we get 6 times 8 squared over 12, which comes out to 32 kilonewton meters, and it's positive counterclockwise. FEMDC, again, is just the same thing but in reverse. For this case, this is 32 negative kilonewton meters, so that's clockwise now. And FEMDE is similar but with a different length. So that's going to be 8 positive on the left, negative 8 on the right, and then our last ones are for this last member, BD. There are no loads in between the joints, which means there are no fixed end moments. So FEM BD equals FEM DB, which equals 0. So those are all our fixed end moments. And again, the 8 kilonewton point load that's at node C, this one here, has no effect on the moments at all because this is not a sway case. If this was a sway case and we were doing a sway analysis using the moment distribution method, then this 8 kilonewton lateral load would come into play. But since this is not a sway case, then it's not, and it doesn't get included in any of the fixed end moments. So the next step in the analysis, the other input we need for these moment distributions, is to find the distribution factors, which is how, if we add a moment to a joint, how is that moment going to be distributed between the different members that frame into that joint. And that moment is always going to be distributed on the basis of the relative stiffness of the members that are in that joint. So for example, if I had a moment at point C, which I am going to do in my moment distribution as part of the process of equilibrating that joint. So if I had a moment at joint C, how much of that moment is going to be taken by CD and how much is going to be taken by CA? And again, that's going to be based on the relative stiffness. Higher stiffness elements take more load. Stiffness attracts load. Good thing to remember in general. So CD, depending on its length and its moment of inertia, right, is going to take a different amount of load than CA. In this case, CA is shorter, which means it's stiffer, and it has a higher I, which also means it's stiffer. So that means CA, we're going to expect that CA is going to take more moment than CD if we apply a point moment at joint C. So in order to find these distribution factors, which are based on the stiffnesses, we first have to find those stiffnesses. So the element stiffnesses for each. Now the first thing I'm going to do is reformulate these I's in terms of a single I so that I don't have to always sub them in. So if I say that I naught is equal to IAC, which is 250 times 10 to the 6 millimeters to the fourth. Okay, so I'm going to say that this number here is equal to I naught. So that's just a parameter. So then IBC is equal to 0.8 I naught. Okay, so BD, sorry, is this one here, which is 200. So it's 200 over 250. This one is 0.8, or 80% of this one. So BD, sorry, this is a mistake here. BD is 0.8 I naught. And likewise, ICD equals IDE, because those two have the same I, these two, 170, is going to be equal to 0.68 I naught. So we're going to need these values when we're determining the stiffnesses. So then find the stiffnesses in terms of I. And I like to keep I naught around because it just makes things a little bit neater when we're doing these analyses. We're not messing with numbers that are times 10 to the 6 in general. So there's two types of stiffness depending on the type of member that we have. The first one is if we have a fixed, and the other one is if we have a fixed pin. Fixed is whenever at both ends of the structure we either have a fixed end or continuity with another member. Okay, so this one is fixed because we have fixed and continuity. This one is fixed because we have continuity at both ends, right? So we have another member there. This one here, AC, is fixed pin because we have a fixed end over here and a pin over here. Now, if we had some pin supporting this, for example, that would not make this element a fixed pin. Okay, it's not what's supporting that element. We can only consider a pin if there's only one element framing into that pin. And basically using this different stiffness for a fixed pin versus a fixed basically shortens the analysis that we have to do. We can do it assuming that everything is fixed, but it's just going to take more iterations, so it's kind of a shortcut. So a fixed member is going to be stiffer than a fixed pin member. And so the fixed pin, so if I'm talking about CA, which is a fixed pin, it's got fixed on this side, pin, which is a rotational release on the other side. For a fixed pin, our stiffness is equal to 3EI divided by L. So this is fixed pin. Okay, so if we increase the I, the moment of inertia, we increase our bending stiffness. If we increase the material Young's modulus, right, which is a material stiffness, we increase the stiffness. And if we increase the length, then we decrease the stiffness, all of which we could expect. So then if I just sub in here, 3E, the stiffness of AC is I naught, right, so I can just put I naught. And the length of this member is 6. So then if I just resolve 3 over 6, I get 0.5 E I naught for AC. Similarly, we have a similar situation for BD, which is also fixed pinned. Okay. Except this time we have a different I, right, because BD is 0.8 times I naught. And then if we solve that out, we get 0.4 E times I naught. And then for CD, which is this top one here, this is a fixed because it's continuity and continuity. So this is for a fixed situation, instead of 3EI over L, we have 4EI over L. So that's more stiff, right? This is fix. So for this case is 4E. The I for CD is 0.68 I naught, and the L is 8. And so we're going to get 0.34 EI naught. Okay, so remember we were talking about how we figured that AC was going to be stiffer than CD. Well, that bears out. AC is 0.5 and CD is 0.34. Then KDE is similar to KDC, which has the same EI but is stiffer than CD because it has a shorter length. So then now that we know the stiffnesses, we can find the distribution factors. Okay, and now the stiffnesses were the same for each element, right? So it didn't matter for each end, it's the same. AC or CA, it's the same, but the distribution factor is different for each member at each joint. So a member at one end could have a distribution factor, a different distribution factor than a member at the other end. But one important thing to remember is, okay, so if we're looking at DFAC, and remember the first here is the near side, and the second is the far side. So A is the near side, C is the far side. So we're looking at AC, and we're looking at the distribution factor for the moment at A for member AC. So if I apply a moment at A, how much of that is going to go into AC? Okay, the answer for a pin is all of it. So distribution factor for AC is 1.0. So that's always the case for a pin where we have one element framing in. So that means that distribution factor for BD, which is also a pin, is equal to 1.0. Now, what about for the fixed end? So we have E here. So ED is the moment at point E, the E end of member DE. So if we apply a point moment here, how much of that is going to go into ED? The answer is none of it, because it can all be accommodated in the fixed end. So the distribution factor for a fixed end, so DF for ED is 0 for the fixed. Okay? And then we can look at it joint by joint. So when we're doing the distribution factors, so if we're doing DFCA, we need to look at the relative stiffnesses of all the members that are framing into that joint. So at CA, looking at the moment in CA at point C. Okay, so if I apply one kilonewton meter of moment here, how much is going to go into CA? How much is going to go into CD? Well, it's based on the relative values of the stiffnesses. So for CA, it's going to be the stiffness of CA divided by the total stiffness. Okay, so DFCA is basically the K of CA divided by the K of all the elements framing into that joint. And for this one, it's CA and CD. And that comes out to 0.5 EI naught, which we saw for up here, divided by 0.5 EI naught plus CD, which is 0.34 EI naught, and that's going to equal 0.595. Then we can do the same thing for the other member that frames into that joint. This is joint C. So that's CD, KCD over KCA plus KCD. So 0.34 EI naught over 0.5 EI naught plus 0.34 EI naught. So that's the total stiffness of all the elements framing into that joint, and we get 0.405. And now one thing you'll notice here is that the sum of these two, all of the distribution factors of that joint, has to equal 1, because all of the moment that we apply at C has to go into one or the other. So all of that moment has to be accounted for. So almost 60% is going to go into CA because it's stiffer, and about 40% is going to go into CD because it's less stiff if we apply a moment at joint C. Now the last joint that we have to look at is joint D, and this one has 3 members. So we're going to get DF, right? So here's joint D. We have DC, DB, and DE. So it's going to be relative to the stiffness of DC over the total stiffness of all 3, or DB divided by the total stiffness of all 3, or DE divided by the total stiffness of all 3. So DF for DC, which is one of them, is the stiffness of DC, EI naught, divided by the sum of the stiffnesses. So it's going to be 3.4 plus 0.4 plus 0.68 EI naught. Right, so that is 3, 4, 4, and 6, 8. So these are all of the members that frame into that joint D. And this is going to be equal to 0.239. Then we can do the other two. Okay, so you'll notice the denominator is the same for all 3 cases, and we're just picking out the first number, the second number, or the third number. And then again, all of these, all the members in framing into joint D, the distribution factors have to sum up to 1. So now we have all of the information that we need in order to actually conduct our moment distribution. So to do that, we're going to basically make a big table, and everybody likes to do this a little bit differently, and textbooks do it in different ways, and I have my own way to do it that I think makes sense. So I'm going to do it that way, and if you like a different way, feel free to do it that way. But I think this one's easy to keep track of everything. So the first thing that you're going to do is have your titles on top of your table. Oops, this is supposed to be member. Okay, so we have joints, we have members, and we have distribution factors. And these are the headings for our table. And I'm going to draw the vertical like this, and we'll extend those as needed. Okay, so we're going to go joint by joint, and each joint I'm going to separate by a vertical line. So for joint A, we only have one member that frames into it, and that's member AC. And I'm going to do it near side, far side, so A, AC. Okay, so I'm always going to do this member by the near side because that's the side that frames into that joint. The distribution factor for AC we found was 1.0. So now I'm done with that joint. I'm going to put a vertical line. Okay, next joint is B. Again, there's only one joint. This is our pin, right? So we have BD, and the distribution factor is 1.0. I'm going to put a vertical line. Okay, I'm also going to mark these as pins so that I remember when I'm doing the analysis that I can't carry over into the pin, and we'll see that in practice. The next joint is joint C, and we have two elements framing into joint C. There's CA and CD, and this is joint C. Okay, so let's draw our vertical line. Okay, and our distribution factors, which we calculated, were 0.595 and 0.405. So it's very handy to have these distribution factors in the table. Then we have joint D, which has DC, DB, and DE. So we have DC, DB, DE, and the distribution factors we determined here. So this is joint D. DC was 0.239, DB was 0.282, and DE was 0.479. And that one is done. And then the last one is joint E, which has only one member, ED. Distribution factor was 0 because this one is fixed. I'll put a little reminder for myself there. So now we've got our table set up. The first step always is to apply the fixed end moments, because these are what are causing our unbalanced moments in the analysis. So the fixed end moments we determined way up here. Okay, so for each one, AC, CA, CD, DC, we have these fixed end moments, and we have to pay attention to what the sign of these is. And we have to be consistent, and we can't lose them, because just like the slope deflection method, if we lose these signs and we don't carry the signs properly, then our answer is going to be completely wrong. So FEM for AC was 9.0, for BD was 0, then we have negative 9.0, so that's the other end of CA, AC, right? These ones are two ends of the same member. CD was 32.0, DC is negative 32.0, so those are two ends of the same member again. DB didn't have anything, DE has 8.0, and ED has negative 8.0. So these are two sides of the same member. So that's fixed end moments, the first one. Now, our method here is that we're going to go through each joint. We're going to release the joint, put it in equilibrium by causing the sum of the moments to be equal to 0. We're going to distribute that moment according to the distribution factors, and then we have to do our carryovers before we move to the next joint. So here I'm going to start, and you can start anywhere you want, although it is a good idea to start with the pins, because we never have to carry over back into the pins. So once we put it in equilibrium, we're basically done with them. So we're going to release A. Again, remember, all of these joints we're considering fixed. So first we're going to release A. To release it and put it into equilibrium, we have to deal with this unbalanced moment. So this has a total unbalanced moment of 9. So in order to bring it back into balance, we have to add negative 9.0. So now this total is 0. Now as soon as I put a joint into equilibrium, I like to put a little double line there, and that signifies that everything above sums up to 0 for that joint. So we've put it into equilibrium, but we can't forget to do our carryover. So we're carrying from the pin into the other end of the member. So how do we find the other end? Well, if we have them just lined up like this, it might not be easy to see, but we know that AC and CA are two ends of the same member. So we're going to carry over, this is CO for carryover, we're going to carry over half of that moment to the other end. So this is going to be negative 4.5. So we keep the same sign, we carry over half. Whenever we're carrying over, we're always carrying over half. So this is because we're adding a moment at joint A. Okay, that moment, in this case, everything goes into AC. Okay, and when we apply a moment to one end, and this side is fixed, right, we're going to end up with another moment at the other end to resist it, right? So that's what the carryover is. So we're adding a moment to one end to bring it into equilibrium, and that causes half of that moment. If this is M, this is half M at the other end. And you can prove this to yourself. We have to assume that this is pinned. You can prove this to yourself using any kind of indeterminate analysis. You could use slope deflection if you like. You can use force method to convince yourself that that's the case. So we do that carryover. So now A is finished. Now, usually I would go and release B, but B is already in equilibrium because it has 0. So there's no unbalanced moment in B. So I'm going to move over straight to C and release C. Okay, so now for C, we have 3 different moments. We have our fixed end moments here. Okay, then we also have this carryover moment. Okay, so that carryover causes another unbalanced force on joint C. So the total unbalanced force is -9 plus 32 minus 4.5, which is the carryover from A. Okay, and this total sum is equal to positive 18.5. You don't have to write this on your table, but I'm writing it here so that you can see for clarity. So if we have a positive 18.5 unbalanced moment on C, in order to put C into equilibrium, we have to add the reverse of this to bring it back to 0, right? Because sum of moments about all joints has to equal 0, right? So we have to add negative 18.5. But how do we add it? We can't just add it to one member or the other, right? And so this is where our distribution factors come in. We have to add this negative 18.5 to balance the positive 18.5. We have to add the negative 18.5 according to the relative values of the distribution factors. So here we have negative 18.5 times 0.595. This is going to come out to negative 11.0, and negative 18.5 times 4.405 is going to be equal to negative 7.5. And once I add those, this joint becomes into equilibrium, and we can check that just by adding up all of the numbers that are above this double line. So if I add negative 7.5, negative 11, negative 4.5, negative 9, and 32, these numbers all add up to 0. So this joint is now in equilibrium. Now, of course, we can't forget that we have equilibrium. We have to do our carryovers. So let's start with CA. CA carries over to AC, but we can't carry over anything into a pin. We can only carry over into a fix. So when we did AC to CA, we were going from a pin end to a fixed end, so that was fine. We carry over half. But if we're going from a fixed end to a pin end, we carry over 0. You can't carry over a moment into a pin, right? So you can imagine if you have a situation like this and you have pin, pin, and you add a moment here, we don't get any reaction moment at the other end, right? Because the pin can't take any moment. It's just going to rotate. Okay, so that's why we don't carry over when we carry over into a pin. There's no carryover factor. But then for CD, that's going to carry to DC. So we can add that one. That's going to be a carryover of a half. So this is negative 3.75. So again, we're carrying over the same sign. We're just dividing it by 2. And that's it for joint C. So now we can move on to joint D. So let's release D. Okay, so now our total unbalanced moment again includes our fixed end forces and our new carryover here. So the total sum of all these three is equal to, if you figure it out, negative 27.75. So now again, we have to balance that by adding a total of 27.75 positive. And if we add a total of 27.75 positive, then this total joint will be in equilibrium. But again, we have to add that extra moment in relation to these distribution factors. So this is going to be 27.75 times 0.239, and it's positive, right, because we're adding the reverse. It's positive 6.63. Then we do positive 27.75 times 0.282, and we're going to get positive 7.83. And this one likewise is going to be 13.29. And then once we've done that again, that means that everything above here is in equilibrium. If I add up all of these numbers, all these 6 numbers, then I'm going to get 0. So now I do my carryover. DC carries into CD. So this is half, so this is going to be 3.32 positive. DB carries to BD. Okay, so I can put a long arrow here, but this is going to be 0 because I'm carrying to a pin. So that's why I thought it was a good idea to put a little pin thing above here, just so that I don't accidentally try to carry any carryover into it. So this is going to be 0, and DE carries into ED, and that's going to be half, so that's 6.65. Okay. So now, what do I do now? Now do I move on to E? Well, no I don't. Because this fixed end, although we're considering all the joints to be fixed at the beginning, this fixed end at E is actually fixed. So we can't actually release it to put it in equilibrium. Basically, any moment that gets carried into ED, which is the end of DE at joint E, any moment that gets carried into that joint sticks there. It's always going to stay there because we can't release it to put it in equilibrium because the joint is fixed in reality. So we're going to skip E. We're never going to release fixed joints. So that's why I put fix here. It reminds me that we're never going to release fixed joints. We can release pins because we have to do that to put these things into equilibrium, but the fixed, because the pin in reality doesn't have a moment resistance, so we can release that easily, but we can't release the fix. So everything sticks there. So 6.65 is just going to stay there. Pin A is in equilibrium already. There's 0. Pin B still has 0, so there's no unbalanced moment, so no point in releasing that. So I'm going to go back to C. Release C. Because C now has a new unbalanced moment, which was caused by this carryover. This is a half carryover. This is a half carryover. Right? So we have this new unbalanced moment. Now we don't going to include all of these ones above, because those together equal 0. We're only going to include this new one here. So this is 3.32. In order to balance it, I have to add negative 3.32, and I'm going to distribute it according to the distribution factor. So this is going to be negative 1.98 and negative 1.34. Okay, this joint is now in equilibrium again, and I'm going to do my carryovers. This one carries over 0 right to AC, so that's 0. And this one carries over to DC. That's going to be half, which is 0.67 negative. So now where do I go? Back to D. So you see now this is where this kind of iterative process comes in, where we're just going back and forth between C and D until these carryover numbers get small enough that we're not worried about it. So I'm going to balance negative 0.67, so I'm going to get 0.16, 0.19, and 0.32. We're back in equilibrium. Do the carryover. So this one here comes half. This is going to be 0.08 positive. This one goes to 0, right, because it's a pin, so there's no carryover, right? That's just like this one here. And this one comes half, and it's going to be 0.16. Okay, and at this point, I can probably stop, but maybe I'll do just one more. Okay, so this 0.08 I'm going to distribute. This is going to be negative 0.05, negative 0.03. I can do my carryovers again. It's going to be 0.02 approximately, negative, and this one's 0. So I think at that point I can probably stop myself and say that I've gone far enough. So how do I know if I've gone far enough? Well, it kind of depends on what the scale of your moments are. So here, the moments, the maximum one is about 32. So, you know, if I get 32.0 or 32.1, it's probably little difference. It's under 1%. So in that case, probably if I get these to below 0.1, then I've probably gone far enough as far as accuracy is concerned. But if my moments, on the other hand, are in terms of thousands of kilonewtons, and then I probably wouldn't have to go to the 0.03 level. If I'm at 1,000 kilonewtons, maybe I only have to go to the 1 kilonewton or to the tens of kilonewtons before I can allow myself to stop. So it's all kind of relative, and you can make that judgment call for yourself. But you'll see now, when I sum them up, the smaller and smaller they get, the less they're going to affect that sum. And I'm only going to do the sum to one decimal place anyways. So once I've gone far enough, the last step is to add up all of the moments at each member end. And that's going to give us the final moments in each member. So I add up all of them. This is a kind of no-brainer. I just look at all of the numbers in each column, all the numbers in this column only, not for the joint, just for the member end, including the fixed end moments, including the carryovers, including the balances, everything. I add up every number in this column, and I put it on the bottom, and that is equal to the final moment at that end of the member. So I just sum up sum of all member ends. And so for this one, okay, I'll just draw these lines down. For joint A, I get 9 minus 9. That's going to be equal to 0, which makes total sense because we know that A is a pin. So the moment actually has to be equal to 0. Same thing happens with B. Now here I'm going to add up negative 9, negative 4.5, negative 11, negative 1.98, negative 0.05, and the total I get is negative 26.5. I do the same thing for this row. 32 minus 7.5 plus 3.32 minus 1.34 plus 0.08 minus 0.03, and I get plus 26.5. And this makes sense because now the sum of all of the member end moments at that joint equals to 0. Fancy that, right? Now that's going to be true at all interior joints. Pins are always going to be 0. Fixed ends don't have this happen, so we're going to see that. If I do the same for all these columns, I'm going to get negative 29.6, 8.0 positive, 21.0 positive. Again, this sums to 0, and here I'm going to get negative 1.19, right? And this is because this is like our fixed end reaction here. Moment reaction at the true fixed end. And that's it. So now I've found all of the moments at the end of the members. Using this information, I can make free body diagrams then of those members. So if I draw those out separately. I know this is quite a long video now, so bear with me. So now I know all the moments. At the bottom there is 0. Here I have 26.5, right? And again, positive. So this one is CA. Right, so this is C, A, B, D, D, E, C, D. Okay, so this was CA was 26.5 negative, which means it's clockwise. Now I can do that for all of them. So those are all of the outputs from the moment distribution method. Then I can draw my external loads, which are also important if I want to use these free body diagrams. So this, if you recall, is 6 kilonewtons per meter. We have the same thing over here. 6 kilonewtons per meter. I have a point load here of 8 kilonewtons and a point load here of 12 kilonewtons. And then using these numbers, I can do the free body diagrams for each member to find the shears. So this reaction here, if I take moment about C, I can find this reaction, which is 1.58. Sum of forces in X gives me this shear, which is in this direction, of 18.4. And I can do the same for the rest. This one here is 23.6. Right, I'm just using sum of moments, and then sum of forces in the Y now for these ones. This is 24.4. So this one is 17.1 up, 6.9 up, 1.33 to the right, 1.33 to the left. And now using this information, I can easily draw the shear force diagram. You notice I ignored the axial loads here because I don't need them to draw the shear or moment diagrams. So here's our shear force diagram. Here's our structure. So our shear goes up 1.58 here, then drops by 12. So this is 1.58. This is 10.42. This one is just 1.33. Try to draw those straight. These are constant shears. 1.33, sorry. And then the shear for the top one. So this one goes up by 23.6. Then we have a distributed load that causes a linear change in the shear, and then it goes up again by 24.4. So this goes up. This is not exactly to scale. 23.6. Down. Okay, then this one is 24.4. And then same thing for this one. This is 17.1 and 6.9. Right, so these come from these shears. 17.1 up, distributed load, and then 16.9 up to get back to 0. We can also find these dimensions, which will be important for the moment diagram. So this dimension here, using similar triangles, is equal to 3.55, and this dimension here, using similar triangles, is equal to 2.85. So then last and finally, I can draw the moment diagram, kilonewton meters, which looks like this. So we have our underlying structure. Now we have no end moment at the pin here, so I'm just going to find this area, which will give me the value at this point. So we have 4.7 at the middle. Then this area brings it back to 26.5, which is the same as the moment that we calculated here. So the shear and the moment are lining up here. For this piece here, we have a linear distribution. So this is a triangle. There we go. That's some sort of triangle. This one is 8.0, so it's 1.33 times the height, right, which I believe was 6. And then for the top, right, we have 26.5 again here. We know that at the other end, we have 29.6 here. Remember that these arrows are always pointing to the compression side. Okay, they can point to the compression side, so when I'm drawing these, I know that if I'm drawing the moment diagram on the compression side, I know which side to draw it on. And then we have this kind of distribution. That looks something like this. This is a parabola. The peak here I can find. So this one was 26.5. This is 29.6. And the peak here I can find by doing, if this is negative 26.5, I add the area of this triangle. I know this distance. So I can get that this is 15.4. Here again, moment points to the bottom, So we know that we have 21.6 here. And we have something that looks like this. Here we have 1.2, which is the value we had at the end, 1.19. And again, we can find the peak using the area of this triangle, and we get 2.8. And that's it. Long story short, that's the way that you can find a moment diagram using the moment distribution method for an indeterminate frame structure without side sway.